We're doing the specimen paper for mechanics from 2020 onwards. Let's begin. A particle P is projected vertically upwards with a speed of 20 meters per second from the ground. Find the greatest height above the ground. Well, okay, when a particle is at the greatest height, we realize, right, that the final velocity of the particle, which is v, is equal to 0. And they've said that the initial velocity, which is u, is 20. And if we're projecting the particle upwards, and this is the direction of the initial velocity, so if this is u, if this direction is positive, then the particle is being accelerated downwards by 10 meters per second squared because of acceleration due to gravity. And so since it's downwards, not only is it 10, but it's negative 10 meters per second. So we can list that as negative 10. And what we're interested in is the height. Now, if you recall which equation relates these four variables, that's right, it's v squared equals u squared plus 2as. And substituting the values, we have s is negative u squared is 20 squared over 2 times negative 10, which is our acceleration. And for that, we have s is equal to 20 meters. Next, they want us to find the total time from the projection, this is key here, until P reaches the ground again. Well, if you remember, S equals ut plus half at squared. Now, when it does return to the ground, this means that S equals 0. We have U, we have A, and we have S, which is 0. And the only thing left is T, which is what we're interested in, the total time. And so if we substituted all our values in, we would get 20t plus half times minus 10 and t squared. So you have 0 equals 20, t minus 5t squared. And so this gives you either t equals 0, which makes sense because at t equals 0 second, when particle P was projected, it was on the ground. Or 0 seconds, or t also equals, 20 divided by 5, which is 4 seconds. The difference between these two is going to give us the time that P took to return to the ground. So we have time taken was 4 minus 0, or 4 seconds. Next question. Constant resistance of magnitude 1350 acts on a car of mass 1200 kilograms. This information is common for both part A and part B later on in the question. So when the car is along a level road, it's moving at a speed of 32 meters per second. Find the power in kilowatt. Okay, power is force times velocity. And since it's moving at a constant speed, the driving force is going to be the same as the opposing force, which is right here. So the driving force is 1350 times its velocity, which is given to be 32. And we have 43.2 kilowatts for that. Splendid. Next question. So they're saying that the car travels at constant speed, but this time the car is moving downhill, which is inclined at an angle of this. Okay. With the engine working at a power of 31.5 kilowatts. Okay. So let's draw the scenario here. If this is our road, say that's the horizontal. That's theta, and here's your car. And so let's model all the forces acting on it. So we have, if you remember the resistance force from earlier, which is this, we have 1350 in this direction. And let's see, we have, in this direction, we have the weight component, which is mass times g times sine of theta. So mass is 1200 kilograms. So 1200 times 10 times sine of theta, this angle right here, theta. And also the driving force. So since I've said that it's moving at a constant speed, what we can say is all the forces acting on the particle or the car are the same. So 1200, that's 12,000, and sine of theta is, they've given it to be 1 over 20 plus the driving force. Well, okay, if power, let's do it on this side. If power is F times V, F is just power over the velocity. So we can rewrite this as the power. Well, we already know the power. It's 31.5 times 10 cubed. That's 31.5 kilowatts divided by the velocity, which is what we're interested in, by the way, is equal to the resistance force, which is 1350. And so if you work out this equation, you will get V equals 42 meters per second. Next up, they're saying that there's 3 small smooth spheres, A, B, and C, with masses 4, 2, and 3 kilograms respectively. They lie in that order on a straight line. So let's model that really quickly. So if this is A, say that's B, and then that's C, okay? And initially B and C are at rest, and A is moving towards B with the speed of 6 meters per second. Okay, so that's the initial velocity for A. Let's mark that as UA. And after the collision, sphere A continues to move in the same direction, but with a speed of 2. So this is the final velocity of A. That's VA. Okay, so they want us to find speed of B after the collision, which is essentially V of B. Okay, so we know that the momentum before the collision is the same as the momentum after the collision. So before that, we have m of A, mass, times initial velocity of A, plus, if you remember, B was at rest. And so that means the momentum of B was 0, which is equal to the final momentum of A and final momentum of B, which is ma times VA plus mass of B times velocity of B. Putting in the values, we have 4 times 6 is equal to 4 times 2 plus 2 and VB. From there we get VB is equal to 8 meters per second. Now, they're saying that sphere B collides with C and they coalesce. This means that they join together and their masses essentially add up to form one giant object, which is D. So, same as before, the momentum before the collision is the same as the momentum after. And so before we have mass of B times velocity of B plus mass of C times velocity of C is equal to the velocity of B and C multiplied with the mass of B plus the mass of C. And so let's see, the mass of B was 2 and 3, so 2 times velocity was 8. And again, since the initial velocity of C was 0, the momentum was 0, and velocity of D, which is velocity of B plus C, is essentially the masses of them combined. So 2 plus 3 kilograms. Velocity of D is equal to 3.2 meters per second. Next up, okay, so they want us to show that the total loss in kinetic energy in the system, because of the two collisions, both collisions, the first of A and B and the second of B and C forming D, is 38.4 joules. Okay, well, the initial kinetic energy was only A was moving. That means that only A had kinetic energy, and so we only need to calculate that, which is half into m of VA squared, so half times 4 times, let's see, it was 6 if I remember correctly, and we have 2 times 36, that's 72 joules. And final KE, after both the collisions, it's we have A moving at 2 meters per second, so we have 4 times 2, plus we have D, mass of D is, let's see, 5 kilograms, times it's moving at, what is it moving at? It's moving at 3.2 meters per second, which is 33.6 joules, if I'm not mistaken. And so the change in KE, or loss in KE, is 72 minus 33.6, which is 38.4 joules. And there you have it. Next up, we have a particle of mass 20 kilograms on a rough plane inclined at an angle of 30 degrees from the horizontal. A force of 25 newtons acting at an angle of 20 degrees above the line of greatest slope of the plane is used to prevent the particle from sliding down the plane. This is key information. The coefficient of friction between the particle and the plane is mu. So they want us to complete the diagram showing all the forces. Well, okay, we have the weight of the particle, which is 20 times 10, which is 200 newtons. And there's a force that's preventing the particle from sliding down the plane. So it means it must be acting upwards. So we can call that, say, frictional force. And there's also a contact force which is perpendicular from the line of greatest slope. So something around here, which is the reaction force. They want us to find the least possible value of mu. First things first, let's resolve all the forces. So resolving, we have, in this direction, we have 25 times cosine of, let's see, 20 degrees. And in this direction, we have 25 of 20 degrees. Okay. Now for the weight, let's see, so in this direction, we have a weight component of 200 sine of 30 degrees. And in this direction, we have 200 cosine of 30 degrees. If we equate all the forces in the 4 axes right here, if we treat this as one axis and then this as the other, let's do this axis first. R plus 25 sine of 20 degrees gives us 200 cosine of 30 degrees. So we have R equaling about 164.7 newtons. And if we do the other axis, we have 200 sine of 30 is equal to F frictional force plus 25 cosine of 20 degrees. From there we have that F is equal to about 76.5 Newton. Now if you remember, the frictional force, friction, really is just mu times the reaction force, which is R. And so for mu, we will have F over R, or as we found the values of them, mu would be equal to 76.5 over 164.7. And so this is roughly around 0.465. Next up, we have a car of mass 1200 kilograms is pulling a trailer of mass 800 kilograms up a hill inclined at an angle of this to the horizontal. The car and the trailer are connected by a light, rigid tow bar which is parallel to the road. The driving force of the car is 2500 newtons and the resistance to the car and the trailer are 300 and 100 respectively. Okay, that was a lot of information to digest. Let's break it down by modeling it on a small diagram. So that's our horizontal and this is our hill. This angle is sine inverse of 0.1, whatever that is. And our car and our trailer are connected by a tow bar. So let's draw all the forces on each of the particles. So for the car, we have its weight, which is 1200 G, or well, 12,000. And for the trailer, it's 8,000 Newton, and reaction forces of each of them. So the reaction force on the trailer, reaction force on the car, and the car is pulling the trailer with force of 1200, with a force of 2500 Newtons. And there's resistive forces on each of them. So on the trailer, we have 100 Newtons, and on the car, we have 300 Newtons. Okay. And also, there's the tension in the tow bar, which is acting on the forward direction for the trailer and the backward direction for the car. There's actually no space, let's bring that down. They want us to find the acceleration of the entire system and the tension in this tow bar. Well, let's start resolving some forces and be on our way. So let's start with the car first. For the car, we have in this direction 2500 newtons, let's see, minus 300 newtons from the resistance, and minus tension, and minus the weight component, which is 12,000 sine, let's see, so 12,000 sine of sine inverse of 0.1. This is just 0.1, so that is just 12,000 times sine of that angle, which is just 0.1. So that's all our forces, right? So we have the driving force, the weight component, the resistance force, and the tension. That is equal to, there's no space here, the mass of the car times its acceleration. Simplifying this equation, we have 1,000 newtons minus tension is 1,200 A. Okay, that's good. Now for the trailer, I'm going to run out of space here. Let's do it below this area. We have the forward force, which is tension, minus the resistive force, and the weight component, which is 8,000. Again, sine of sine inverse of 0.1 is just 0.1, is equal to mass times acceleration, which is 800 A. Simplifying, we get P minus 900 is equal to 800 A. And so we have our two equations, 1 and 2. If we add them, we get, let's see, so the t's will cancel out, and we have 1,000 minus 900, and on this side we have 2,000A. So 1,000 minus 900 is equal to 800 plus 1,200 is 2,000A. And so A is equal to 100 over 2,000, which is, let's see, 1 over 20, or 0.05 meters per second squared. Plug that into I, and we get T is 940 Newton. Okay? For the next part, they're saying that the car and trailer stop traveling when the speed is 30 meters per second. So that's our initial speed. And the driving force becomes 0. And they ask us to find the time before the system comes to rest. So this means that the final velocity will be equal to 0. And they want us to find the time. And so the only piece of information that we're missing is the acceleration. And so how will we find the acceleration? Well, we know that the resultant force is equal to mass times acceleration. So if we resolve all the forces for the system, then we have, actually let me get the diagram first. And so here's our diagram from the previous page. In this second part of the question, they've removed the driving force of 2500 newtons. And now if we treat the entire thing as one system, as one particle, if this was just one particle, then we would have its mass being 1200 plus 800, or having a weight of 20,000. 1200 plus 800 is 2000. So 2000 times G. And we will have a combined resistive force of 400 newtons. So resolving the forces, we have the weight components, which is, let's see, 1200 plus 800 times the sine, well, the sine of sine inverse of 0.1, which is just 0.1, and the resistive forces of 400 newtons, because 300 plus 100, and that's equal to mass, which is 2000 again, times the acceleration. And so from here, we have acceleration is equal to 1.2 meters per second squared. But remember, the acceleration happens in the downward direction. Since the initial velocity of 30 meters per second was in the upward direction, that means the acceleration must have a negative sign. And now we have A, V, U, and T. And so the Suval equation that connects those four variables is V equals U plus AT. And our final velocity is 0, initial is 30, while our acceleration is minus 1.2 times the time. And from there, we get time equals 25 seconds. Now for the second part, where they want us to find the force in the tow bar, or the tension in the tow bar, if we resolve the forces on one of the particles, the car or the trailer, let's do the trailer, we will see that tension minus 100, so tension minus 100 minus the weight component, which is 800 times 0.1 times g, which is 10, is equal to mass times acceleration. So 800 times minus 1.2, because acceleration happens in the negative direction. Simplifying, we will get tension is equal to 60 newtons, but not just 60 newtons, it's a negative 60 newtons. This means that the tow bar is pushing the trailer downward, which is why we get negative 60 newtons. The tension here isn't actually in the upward direction. So if you see something like this in the exam, don't think that this is wrong, because all the negative is saying is that the direction of the tension is opposite to the direction we initially thought it was in. Next question, we have particle P moves in a straight line, and the velocity at time t is given by these three equations, depending on what time we're talking about. So from 0 to 4, we model it with this equation. From 4 to 14, we have v equals k. And lastly, we have from 14 to 20, we have this equation that models the velocity, where k is a constant. So they want us to find that constant k. The velocity at time t equals 4 is going to be the same at both of these equations. So at t equals 4, v equals 5 times 4 times 4 minus 2, which is also equal to k, and so k is equal to 40. Now they want us to sketch the velocity time from 0 to 20. So let's start by drawing our axes like so. From 0 to 4, we're modeled by this quadratic equation, and if you find the roots of this, you get t is equal to 0 or t equals to 2. So at t equals 0 and t equals to 2, this graph, this quadratic equation, will intercept the line v equals 0. So it's going to be a quadratic graph that looks something like this, something like that. And since quadratics are always symmetrical, from the vertex is on the midpoint of these two x coordinates. So this time is equal to 1. And obviously this goes on until t equals 4. So somewhere around here. Do that in red, somewhere around here. From t equals 4 to 14, we have v equals a straight line, which is k equal to 40. So it's going to be a straight horizontal line, like so, up until t equals 14. And from t equals 14, we have this equation, and it stops at t equals 20. So let's double check where that lies. So v equals 68 minus 2 times 20, which is equal to, let's see, 40. So that's 28. So it only goes down until 28. So if this is roughly 40, so 28 is going to be somewhere around here. And so something like that, with this x coordinate being 20. And that is it. That's our graph. It doesn't have to be to scale, as long as it's an appropriate representation. For the next part, they want us to find the set of values for which the acceleration or the gradient of the v by t graph is positive. And so we can see that in this part, the gradient is 0. So acceleration is 0. And in this part, the acceleration is negative because it's a downward sloping curve. We want it to be positive sloping, which actually starts from here and ends at here. But how do we show that? Well, we have to find an expression for a in terms of t by differentiating this. So a is equal to rate of change of v with respect to t, which is, let's see, that's 5t squared minus 10t. So it's d by dt of 5t squared minus 10t, which is just 10t minus 10. And so the acceleration starts being positive after reaching 0, which is here. So if we set the acceleration equal to 0, which is 10t minus 10, we have t equals 10, just reconfirming our hypothesis that this is where the acceleration starts being positive. And it ends at this point, which is t equals 4 seconds. So our answer is t is more than 1 second, but it is also less than 4 seconds. Why not less than equal to or more than equal to? Well, because at this point exactly, the acceleration is 0. So this point does not have a positive acceleration. Similarly, at this point exactly, acceleration is again 0 because of the straight horizontal line. And so this point is not included in our set. In the final part, it might be a little tricky to catch sometimes. They want the total distance and not the displacement, by the way. The distance traveled by p in the time interval of 0 to 20. So what they essentially want is the area covered by these lines and the x-axis, this area. We can find this area by using the formula for a trapezium and a rectangle. But what about this area and this area? The trick here is to see that this is going to be a negative area while this is going to be a positive area. And so if we were to integrate from 0 to 4 in one go, we would have some area minus some other area, and that would just give us the displacement, not the distance. So to overcome that, what we have to do is we have to integrate from 0 to 2 and take the absolute value of that, and then to that add this area right here from 2 to 4. So let's write all that down. So we have the integral from 0 to 2 of velocity with respect to t, and so the absolute value of that, because that's going to be a negative area, plus the integral from 2 to 4 of velocity with respect to t, plus the area of that trapezium that we were talking about. So let's see. This height, this distance is 28, and this distance is 40. Whereas this distance is 14 minus 4, which is 10, and this distance is 20 minus 14, which is 6. So we have the area of the trapezium, so half times a plus b times the height, which is 20 minus 14, and the area of the rectangle, which is just the height 40 times its base. And so the expression for t was 5t squared minus 10t, absolute value of that, plus this. And let's see, this is going to be 604. And so if you evaluate these integrals, we have something like this. Let's see, so 5 by 3 minus 5t squared, 0 and 2, absolute value of that again. And then again, finally, t cubed minus 5t squared, 2 and 4, plus 604. And that should give you 644 meters. And we're done with this question. For question number 7, this is the scenario. Two particles A and B of masses 0.8 and 0.2 kilograms respectively are connected by a light inextensible string. Particle A is placed on a horizontal surface while the string passes over a small smooth pulley P fixed at the edge of the surface. B also hangs freely. Okay, the horizontal section of the string AP is 2.5 meters long, and the particles are released from rest with both sections of the string. So AP and PB, both sections of the string, taut. So what that means is the acceleration experienced by both A and B is the same. Given that the surface is smooth, find the time taken for A to reach the pulley. So if we think about the entire system and we resolve all the forces, you will see that the system is being pulled in this direction by a force of 0.2 g because of the weight of B. So if this is the positive direction, downwards is the positive direction, we have 0.2 g, and that is equal to mass times acceleration. And the mass of the entire system is the mass of A plus mass of B, so 0.2 plus 0.8 kilograms mass times acceleration, which is our acceleration. From here we get acceleration equals 2 meters per second squared. And so we have the initial velocity of A, which is 0. We have the acceleration, which is 2 meters per second squared. We want the time taken, and we also know the distance that A is going to cover, which is 2.5 meters. What's the equation that connects all these four variables? That's right, S equals ut plus half AT squared. Put all the values in, and you get t is equal to square root of 2.5, which is 1.58 seconds. Notice how we assume that there was no frictional force on A in this direction. Why is that? Well, that is because in the question they said the surface is smooth. When they tell you that the surface of anything is smooth, you always assume that there is no frictional or resistive forces acting on any masses. On to the next part of the question. They're saying it is given that instead the surface is rough and that the speed of A immediately before it reaches the pulley is v. The work done against friction as A moves from rest to the pulley is 2 joules. Use an energy method. Whenever they want us to use an energy method to find anything in mechanics, you always have to take into account the potential energy and the kinetic energy. So what we see is the distance moved by A, which is from here to here, that's 2.5, is going to be the same distance moved by B from here to say here, which is also going to be 2.5 meters. That way, we can calculate the potential energy loss of B. Since they're saying that the energy lost as friction is 2 joules, we can write this as gravitational potential energy lost by B will be the same as the kinetic energy gained by, notice, both A and B gain kinetic energy. B speeds up and because it's accelerating, right? And so does A. And since both of them gain kinetic energy, we're going to say that GP lost by B is the same as the KE gained by A and B. And since work is done against friction, some of the GPE is also converted to thermal energy. And so let's see, the GPE is going to be mass of B, which is 0.2, times G, times the vertical distance B covers, which is 2.5 meters. And the KE of the entire system is going to be half times mass. It's a combined mass of A and B, because we're talking about the system. So 0.2 kilograms plus 0.8 kilograms times the difference of the final velocity squared and the initial velocity squared, which is 0. And of course, plus 2. If you simplify, you get this, and simplifying even further, we have V is equal to square root of 6, which is approximately equal to 2.45 meters per second. And we are done.